Welcome back. Let's define what a cycle is. So a cycle is just a notation for certain types of permutations. Let S be a set and alpha be in the symmetric group of permutations of S. That is, alpha is a permutation of S. The permutation alpha is called a cycle of length m if there are elements a1, a2, am in S, that is, there are m elements in S, such that alpha evaluated at ai is ai plus 1 mod m. So we are taking mod m, we are taking the index I plus 1 mod m here. And alpha fixes any x in S that is not equal to one of the a's here. So let me explain what we mean by this. So basically, when we have a cycle alpha, it is written in this notation a1 comma a2 comma am. So notice that alpha is a cycle. It means that the alpha evaluated at a1 is a2, alpha applied to a2 is equal to a3, and so on. Alpha applied to am minus 1 is equal to am, and then alpha applied to am is equal to a1. So at the end we have this wraparound, which is indicated by this mod m. That is, when I is m, then you have m plus 1, and m plus 1 mod m is 1. So that's why this mod m is written in the index. So when alpha is applied to am, we get a1. Note that we may also write the so this cycle here. So this is a permutation where a1 goes to a2, a2 goes to a3, and so on, and at the end am goes back to a1. Now this same cycle can be written as a2, a3, am, comma a1. Notice that this cycle here is the same as this cycle here. As permutations, they are the same. Why? Because if you look at it, a1 goes to a2, a2 goes to a3, a3 goes to a4, up to am, which is exactly the same as here. In fact, the notation for a cycle of length m may be expressed in m different ways. So notice that I could also express this. So basically, I can also express this cycle by writing. I can start with a3 and then go to a4, a5, am, a1, and a2. So there are, I can, the same, if I have a cycle of length m, I can express it in m different ways. The permutation alpha, which is given by this table, and we can express that as a cycle and see how. So notice that I'm going to start with 1, and then I see that 1 goes to 4, and then 4 goes to 2, and then 2 goes to 3, and 3 goes back to 1, and then 5 is fixed. So the alpha can be expressed as a cycle in this way. So 1 goes to 4, 4 goes to 2, 2 goes to 3, 3 goes back to 1. And notice that this cycle can be expressed in 4 different ways. So 1, 4, 2, 3, that's how I wrote it here. And then I can also rewrite that as 4, 2, 3, 1. And also rewrite that as 2, 3, 1, 4. And also 3, 1, 4, 2. So notice that these 4 cycle notations, they give us the same permutation. So if we, for example, if I write this in tabular form, I'm going to get the same alpha here. So this is telling me that 1 goes to 4. Okay, 1 goes to 4. This is telling me that 2 goes to 3. 2 goes to 3. This is telling me that 3 goes to 1. So 3 goes to 1. It's telling me 4 goes to 2. So 4 goes to 2. So this is exactly the same as alpha. You can check that each one of them is the same as alpha. So keep in mind that if we have a cycle of length 4, we can express that in 4 different ways. And if I have generally a cycle of length n, we can express that n different ways. So this is kind of explains, this picture here explains why we are. So we basically notice that to go from this cycle to this cycle, I am basically pushing the so we are basically pushing the elements here to the left with the wraparound at the end. So 4 is coming in the place of 1, 2 is coming in place of 4, 3 is coming in place of 2, and then 1 is taking the place of 3. So we are shifting to the left. So if I shift these guys to the left by 1 place, then I'm going to get this, where keep in mind that we are wrapping around at the end. So if we shift these guys to the left again by 1 place, then we're going to get 2, 3, 1, 4. And if we shift again, we get this. Clearly, if I shift one more time, I'm going to come back to this this cycle here. So that's what's expressed in this table. So you have A1, A2, A3, A4, A5, all the way up to A10. So let's say the cycle is A1 goes to A2, A2 goes to A3, so on. A10 goes back to A1. Now we can shift everything. So here I'm writing A1 here, A2 next, and so on. And if you follow the arrows, we still basically have the same cycle. Okay, so I'll let you investigate this picture to see why a cycle of length n has n different representations. Now, if we have a permutation alpha, we can express that by using graphs in the following way. So here's a permutation alpha on the set of integers 1 up to 12. So we're gonna make a graph like this. So I'm gonna start with 1. 1 goes to 2. So 1. So I'm putting the arrow. So the value of alpha at 1 is 8. So 1 goes to 8, and then notice that 8 goes to 6, so 8 goes to 6, and then 6 goes to 9, so 6 goes to 9, and 9 goes back to 1, so 9 goes to 1. So we have completed a cycle here, 1 to 8, 8 to 6, 6 to 9, 9 back to 1. Okay, so now if I start back at 1, I'm going to keep wrapping around in this loop here. So now let's start with the next number that hasn't been used yet. So 2. Well, 2 goes to 2, so then basically 2 goes to 2, so we're done. Next number that we haven't used yet is 3, so notice the 3 goes to 10, and then 10 goes to 3, so 3 goes to 10, 10 goes to 3. Okay, the next number would be 4. 4 goes to 11, 11 goes to 12, 12 goes to 7, 7 goes back to 4. So we get this loop here. And then the last number is 5, and 5 goes to 5. So this is what's happening. So notice that exactly one at each vertex, exactly one incoming and one outgoing arrow. So we have exactly one incoming and one outgoing arrow at each vertex. So this permutation alpha, basically what we got is that we can express alpha as a product of cycles, disjoint cycles, in fact. So we can write alpha as this cycle multiplied by this cycle. This is a cycle of length 1. Now a cycle of length 1 is essentially the identity permutation. That is, it fixes everything, right? It takes 1 to 1, 2 to 2, 3 to 3, and so on. So recall that if I have a cycle, if the cycle is missing any one of the elements, it means that element is fixed. So 3 and 10 here, 3 goes to 10, 10 goes to 3. So this is a cycle of length 2. This is a cycle of length 4, and this is a cycle of length 1. Now again, a cycle of length 1 is just the identity. Then we don't have to write that. So we can express alpha as the cycle 1869 multiplied with the cycle 310 and the cycle 411, 12, 7. So the alpha can be expressed as the product of disjoint cycles 1869, 310, 411, 12, 7. Notice that these cycles are disjoint. That is one element doesn't appear in more than 2 cycles here. So note that we customarily skip the cycles of length 1. Again, if I have a cycle of length 1, for example this one, then this is basically fixing all the elements, right? So 2 goes to 2, but then 1 goes to, so 1, none of the other, so in this cycle none of the other elements appear, so that means that they are also fixed. So we don't have to write these 1 cycles. You can check that if you take the composition of these 3 permutations, you will end up with alpha. So let me check one of them. So let's say what is this doing to 1? Well, this cycle right here, what is it doing to 1? Well, 1 doesn't appear here. That means that 1 is fixed. So 1 goes to 1. Well, 1 goes to 1. So what is this doing to 1 then? Well, this 1 doesn't appear here as well. So 1 goes to 1 by this one. Well, finally, this one moves 1 to 8. So 1 goes to 8. So this product moves 1 to 8. So that's exactly what alpha is doing. So you can check one by one that this product is the same as alpha. And here's your exercise to express this alpha as a product of disjoint cycles. So what do I mean by disjoint cycle again? So if sigma is a cycle of length k, a1, a2, dot 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 ak, tau is a cycle of length m, b1, b2 up to bm. Let's say these are cycles in the group of permutations of S for a set S. Then sigma and tau are disjoint if ai is not equal to bj for any I and j, where I is between 1 and k, j is between 1 and m. That is, none of the elements, none of the a's appear in tau and none of the b's appear in sigma. So that's how they are disjoint. Disjoint cycles always commute. That is, if alpha and beta are disjoint cycles, then alpha beta is the same as beta alpha. So if I go back here, this is a product of disjoint cycles. So if I rearrange these cycles, it doesn't change the outcome. So disjoint cycles commute. Every permutation of a finite set can be expressed as a cycle or a product of disjoint cycles. Every permutation of a finite set can be expressed as a cycle or a product of disjoint cycles. And which is what we did in this example. We expressed alpha as a product of disjoint cycles, and the proof of this is pretty much follows the way we expressed alpha as cycles. But I want to go over the proof here. So if we look at the if we look at beta here, then we can express beta as a product of cycles, and so notice that, okay, so here I'm starting with the 2 here, so 2 goes to 3, 3 goes to 1, and then 1 goes to 5, and then 5 goes to 2, so we get this cycle. 6 and 4 left, so 6 goes to 4 and 4 goes to 6, so we got this. Now that's the same as this. So notice that there isn't any difference because the 2 cycle 6 4 and the 2 cycle 4 6 are the same, right? 4 goes to 6, 6 goes to 4, and then 3 1 5 2 and 3 1 5 2, that's the same as this one, so these two are the same. And remember that the disjoint cycles commute, so I can express beta in these two ways. Let's say alpha is this product of cycles and beta is this product of cycles. Now, since this one is a cycle of length 1 and this is a cycle of length 1, we really don't have to write them because they are just the identity permutations. Each one, so this any one cycle is just the identity permutation. So when we take the composition, it doesn't. We don't really need to write it. So what is alpha times beta? So let me check. Alpha times beta. So I have to. So I'm going to start with 1, and I'm going to apply beta to 1. If I apply beta to 1, notice that this one and this one does not change 1. So this is a cycle that changes 1. So 1 goes to 2, and then here 2 is fixed. 2 is fixed here. 2 goes to 7. And 7 is fixed here, so 2 goes to 7. So if I start with 1, 1 goes to 2, 2 goes to 7, so 1 goes to 7. Now I start with 7. Again, 7, so beta takes 7 to 1, and alpha takes 1 to 3, so 7 goes to 3. Now 3 goes to 7 here, 7 goes to 2 here, so we see that 3 goes to 2. And then 2 goes to 3 here, 3 goes to 1 here, so 2 goes to 1, so we get this cycle 1 7 3 2. The element that's missing here is 4, so we start with 4 again and we repeat the process. So you can see that alpha beta can be expressed as a product of disjoint cycles here, where we have 3 cycles here. So let alpha be this permutation and let beta be this permutation. We want to express alpha beta in cycle notations, and then express alpha beta, alpha times beta in cycle notation, and then convert alpha beta back to array form or the table form. Well, if you look at alpha, then alpha 1 goes to 2, 2 goes to 1, so that's going to give us a cycle of length 2. 3 goes to 3, so we don't have to write that, and then 4 goes to 5, 5 goes to 4, so we get a cycle 1 to 2, 2 to 1, and we get a cycle 4 to 5, 5 to 4. So alpha is basically a product of 2 disjoint cycles. One of them has 1 2, the other one has 4 and 5. And then similarly, you can express beta as a product of cycles, and then you can multiply them. So for example, how do I get the cycle 1 4? So if I start with 1, so I apply beta to 1 first. So beta applied to 1 is 5, alpha applied to 5 is 4, so 1 goes to 4. Now where does 4 go? Well, beta applied to 4 is 2, and 2 goes to 1 here, so 4 goes to 1, so 4 goes back to 1, so we get a complete cycle here. And then if I start with 2, notice that beta applied to 2 will be 4, and alpha applied to 4 is 5, so 2 goes to 5. Now let's apply alpha beta to 5. Alpha beta applied to 5, so beta applied to 5 is 3. Alpha applied to 3 is 3, so 5 goes to 3. Okay, alpha beta applied to 3. Beta applied to 3 is 1. Alpha applied to 1 is 2. So 3 goes back to 2. And we have completed the cycle. So we are done. There are 5 symbols here, and all of them have been accounted for. So alpha beta is equal to that in cycle notation. And you can write express alpha beta in a table by just looking at this. So you can say 1 goes to 4, 4 goes to 1, 2 goes to 5, 5 goes to 2 goes to 5, 3 goes to 2, and 4 goes to 1, and 5 goes to 3. So you can express that in a table. All right, so I'm going to stop here, and we'll continue with the definition of the identity permutation.